Hello, so this is my review of lecture 21 on eigenvalues and eigenvectors. So this is the first chapter where eigenvalues and eigenvectors are introduced, so it's quite an important one. And these 3 points here that I'm going to discuss is also a crucial things that will be used throughout the rest of the chapter. I think until chapter 24, 25 we'll also use that. So let's get on with it. So first, what is the eigenvector? So matrix A is just a matrix, let's say a nice example 3 by 3 matrix. And when it multiplies one vector, you just imagine that it just acts on X, right? The matrix A acts on this vector, so it will give us, so imagine this is a 3 by 1 for sure, a column matrix, and this will give us let's say B, a new vector B. So imagine like in the 3 coordinate system like this, it's pretty ugly coordinate, right? Let's say this is our initial vector X. It should not be named, let's call this A, okay, for the sake of clarity. And then we have that XYZ, okay, and then we have our A here, and then when we multiply this A by the X, I mean the capital A, the matrix, then we will end up with some kind of matrix B that points here, for example. I'm not sure. So it looks like just like it's a function that accepts A as a variable and then it outputs B. Okay, so that matrix A is like a function. And imagine this vector B. It could end up in any places, in any kind of direction. You could end up here, you could end up here, you could end up here, but you could also end up in the vector that is parallel with A, parallel with A, or that initial vector. So parallel, what does parallel mean? It's just like you're stretching A. So this is, remember, this is our A, and then even when you multiply those A by the matrix big A, you end up with some vector B, but they're pointing in the same directions. And you just need to like stretch them. In other words, you scale those matrix A by some scaling vector that we will call lambda. So these are the main idea, the gist of this eigenvalues and eigenvector. So this lambda here is our eigenvalues, which are that scaling vector, and then B, in our example B, which is also equal to A because they're pointing in the same direction, therefore having the same component of a vector. This is our eigenvalues, okay? Eigenvector, that's what I want to say. So this brings us together to our most important formula here, the AX some matrix times an eigenvector here equal to some eigenvalues times that eigenvector. Okay, so remember that one. And then this brings me to a second point. Imagine here, how about if I say that B ends up perfectly on top of A, exactly here. Now in this case, it's just A equals A. So what is the eigenvalue here? The eigenvalue here is just 1. But it's also possible where the eigenvalue is 0. So you have some matrix A. From now on, let's use the notation X here. Then you multiply X, you end up with the eigenvalue of 0 times X, which means that the AX is 0. So that means the eigenvector itself is in the null space of A, right? Because remember null space that we learned from earlier chapter, that this equation, if there's a non-zero solution for x, that means x is our null space of A. So the point here is that eigenvalues 0 is nothing, there's nothing special about 0 of being eigenvalues. And there's also one more fact, including the fact that usually there are multiple eigenvalues. So for 2 by 2 matrix, like nice symmetric 2 by 2 matrix, for example, this matrix, for example, this will have two distinct eigenvalue. So one of them can be 0, of course, and one of them can be something else. Although, you know, in the symmetrics, it could not be have an eigenvalue of 0. This is my bad example. But let's say, okay, let's say any kind of matrix. You will learn later on that only singular matrix are sure to have the eigenvalue of 1. But what the point here is that imagine like n by n, 5 by n, you can have that eigenvalue 0 and there's nothing special about it, you know, because we're not interested in only one, we're interested in all the eigenvalues that is inside this matrix A. Okay, so that clears up my second point. Now let's talk about how to get those eigenvalues and eigenvector. Let me clear up the board a bit. So let's start with our lovely equation. And the step is first to find eigenvalues. And the second step is to find the eigenvector. So the trick is to move this into the left hand side. And then you pull out those x's. But then remember that lambda is a scalar value, so you cannot subtract this from A, so you need those in form of the matrix. So that's why we use identity matrix, which is like the equivalent of 1 in the matrix world. Okay, so since this is a scalar, this is also equal to if you switch the order, that doesn't matter. So let's see. So we have two probability here. So either this is 0 because this will be equal 0, or this one is 0. But this one is 0. If we're talking about this case, this will be really boring and trivial because this will gain us no information. Of course, like all A, any kinds of A, if we solve this and then we assume x is 0, then that's it. That's the eigenvector is always 0, but that's not the case that we're interested in. In case we're interested in a non-zero solution, so you want this x to be non-zero, and this matrix cannot be 0, right? It can be 0, but then most cases it won't be 0. So we need this x that when it got multiplied with the matrix, with this kind of matrix, it brings us to 0. So non-zero of x. So what kind of theory that support this fact? You are right. So these are the null space of A minus lambda identity. So I is the identity matrix here. So the x is the null space of matrix A minus lambda I. Okay, and what do we know so far about if there is a non-zero solution of some matrix in the null space? This means this matrix is a singular matrix, right? It's a matrix with a dependent column or dependent row, you remember? So if you can have for example like this, so this is a singular matrix because this is the rank of it is less than 2. So I hope you remember. If not, please review earlier chapter where we'll talk about the singular matrix. So we have that new fact of this is singular matrix. And what do we know about the singular matrix? We know that the determinant of it is also 0. So this gives us enough information to start computing the eigenvalue. So it's just pretty simple. It's just let's say in 2 by 2 you have this, and then you multiply by some by this equation, and you subtract this lambda from the matrix A, so you end up with let me give us some space here, A lambda 0 0, and D minus, this should be B and C, and then you compute the determinant of this, and then you will solve you will find the root of the equation, which is the lambda, and we will talk about some examples in the next part. So that's it. Thank you.